Okay, so in section 2, what we're going to do is we're going to start looking at what a definite integral is. And the way that we do that is we look at the sums of those little rectangles of area under the curve. And in order to really understand what's going on, what we're going to talk about is a Riemann sum. And again, with Riemann sums, you want to be familiar with summation notation. So basically what we're going to do is we're going to take sigma, which is this Greek guy right here, and we're going to have some formula that we're going to use. And with that formula, we're going to start at this number, and we're going to put it into the formula and do our math, and then we're going to stop when we get to that top number. And so this is summation notation. So just a really quick reminder on this. My formula here is 3k minus 1, and I'm summing from 1 to 4. So I'm going to have 3 times 1 minus 1. Okay, that's one of my guys. And then I go to the next number, which I start at 1, I'm going to 4, so I'm going to put a 2 in for that k. So I'm going to have 3 times 2 minus 1 plus 3 times 3 minus 1 plus 3 times 4, and I stop at this one because I've hit the 4 minus 1. And when I sum all these guys up, I've done my summation notation, and I'm going to get the answer to this question. So this is going to be 3 minus 1, which is 2, plus 6 minus 1, which is 5, plus 9 minus 1, which is 8, plus 12 minus 1, which is 11. So I'm going to sum these guys up. I get 7 plus 19, which is 26. So that's how this summation notation works. Well, a Riemann sum, which is this guy right here, a Riemann sum, they're used to help find the area under the curve, which is what an integral is. It's an area under the curve. They can be positive or negative depending on the function. So like for our particular problem, the answer we got was a positive answer. You could just as easily get a negative answer, and that's okay. And what they do is they find the areas of rectangles. Remember, the area of a rectangle is height times width, or length times width, or whatever, however you want to call it. It's the two dimensions that make it up. Well, here it is. The function of x, that's my height part, okay? And delta x, that's my width part. So what I'm going to do is I'm going to figure out how many rectangles I want. Well, that's this n number. So I'm going to start with at least one rectangle. I'm going to stop in the nth rectangle, and I'm going to add up all those areas. And that's all this is right here. That's all this is. This is my width right here. And this is my height right here. That's all the notation stands for. And that's how a Riemann sum works. And when we're talking about a Riemann sum, that n value on the top, this guy up here, is going to be the number of subintervals or the book also calls them partitions. So this is the way that the Riemann sum works. We split our function up into n number of partitions or subintervals, and then we add up all those areas of the rectangles that we've created. It's really, really an interesting, cool thing. And don't let it be hard, okay? It's going to look different, but this is all going to make sense once we see what that integral actually does, okay? So hang in there and just be familiar with what the Riemann is doing, okay? The Riemann sum is helping you to find the area under a curve, okay? And how are we going to do that? With rectangles. Okay, so now what we're going to do is we're going to take these Riemann sums that were on the previous slide here, and notice here's those Riemann sums again, okay? See them right there? There they are. Well, now what we're going to do is we're going to take the limit of those sums, and instead of saying, I want 10 subintervals, or I want 12 subintervals, or I want 5 subintervals, what we want to do is we want to let the number of subintervals increase towards infinity. Okay? We want to let the number of subintervals increase toward infinity. And this is important because remember on the previous section of notes, as we increase the number of subintervals to find the area under a curve, it became much more accurate. So what we're going to do is we're going to let this n right here go all the way to infinity. We're going to look at an infinite number of partitions. Well, what does that mean? That means that for a definite integral, all continuous functions are going to be integrable, okay? In other words, we can take an integral of anything that's continuous, okay? Number two, if a function is continuous on a closed interval, then the definite integral exists. So if we are looking at just a specific part of a function and it's continuous on that specific part, then we can find a definite integral for that part. And so the definite integral looks like this formula right here. So, you know, don't be discouraged. This looks like a nasty formula, but it's all going to work out really well. So what does this formula mean? Well, it means the integral. And when you take an integral, then you're looking at this guy right here. This is your integral notation, okay? And we're going to spend the next 2 months working just with integrals. So we're going to spend a lot of time talking about them and some things that we've got to be aware of. Number one, we've got to be aware of the upper limit of integration. Okay, that's the b part. The upper limit of the integration is the b part. This guy right here. All right. The lower limit of integration, in other words, the part where you start, okay, that's going to be that bottom number down here, this a guy. So the upper and lower limit of integration tell us what interval we're interested in finding. Okay, the integral sign is this elongated S-looking thing. This guy right here is this looks like an S. Okay, so anytime you see this stretched out guy right here, this is an integral. And then we're going to just put our function in here. So this is the integrand or our function. And there's that guy right there. And then the variable of integration. So is it x, is it y, is it z? What is it? And you read this by saying the integral of f, function of f, the integral of x squared from 2 to 7, the integral of the sine of x dx from 0 to pi over 2. So this is what an integral is going to look like. All right, so it's a lot of notation going on here, but you're going to see it a lot in your near future. So don't be panicked by this. If you have a question, ask. But you're going to see this a whole lot, so don't sweat this too much. Okay, so here's how it's going to work. What you're going to do is you're going to have a question, something along the lines of the interval from -1 to 3 is partitioned into n subintervals of equal length, delta x, which is equal to 4 divided by m. And we're going to let m sub k denote the midpoint of the kth subinterval, express the limit as an integral. Well, remember in section 5.1 that we discovered that the midpoint guy, and that's wrong, that is not the highlighter, the midpoint guy was the one that was best suitable to find an accurate area of a rectangle. So we're going to continue to use that guy. And we want to express this guy right here. We want to express this guy right here as an integral. Well, we want to go from 1 to 3. So if we're going to go from 1 to 3, then we're going to have something that looks like this. And we're going to go from -1 to 3. Okay? And then the mk squared part and the mk part. That is your variable right here, this dx. And so the integral then is going to set up to be 3x squared minus 2x plus 5. And the function that we're using is going to be dx. All right, so instead of making the delta, we'll just say dx. And that's all there is to it. That's how you show the integral of this particular guy. Okay, remember a few key things here, and we're going to talk about it a lot, but definite integrals are also used to find area under a curve, and that's been mentioned several times. So what we want to do is we want to look at where f of x is non-negative, okay, in other words, all the values for y are positive. We want to look at f of x where it's integrable on the interval from a to b, so in other words, it's continuous. We can take an integral of it. And we're going to look at the area under the curve from a to b as the integral of f of x. So we're going to look at this guy right here as our integral. Okay. Well, Find the area under the curve of the following function. Well, looky here. We've got 4 minus x squared dx, okay? And here's a graph of what it looks like, and we want to find the area in this spot right here under the curve. So we want to find all the area that's under here. Well, pay attention to what you're looking at here. We've got a semicircle, okay? So how do you find the area of a semicircle? And this is where the calculus is going to lead us at some point in time, but we don't know exactly how to solve this guy out today. We haven't learned all our tips and tricks on this yet, but we do know that this guy right here is a semicircle. And I can find the area of a circle, okay? The area of a circle is pi r squared. So if I'm working with a semicircle here, let me just remind us this is a circle. So if I'm working with a semicircle, then the area is half of that, or pi r squared over 2. Okay? And so what do I need to do? I need to figure out what my radius is. Well, look at this guy right here. I'm centered at the origin. Red is not going to show up. Let's try green. I'm centered at the origin, and I have a radius out here of 2. So this integral right here can be solved by substituting a radius of 2 into my semicircle area formula. So the area would be pi r squared divided by 2. All right, so what is this? Well, this is the area, which is equal to 2 pi. Okay, that's our answer. Well, what does this guy equal? This guy right here, this integral from -2 to 2 of the square root of 4 minus x squared dx is equal to 2 pi. And that's all there is to it. So if you've got an integral of a graph of something that you can use the area on, then do that right now. It'll help you out, and it'll give you a good understanding of what's going to be coming later. All right, what to do though if you've got negative areas. So if you've got an integrable function and it's non-positive, so all the y values are negative, the area of the rectangles will be negative, okay, because they'll all be under the x-axis. So to account for this and to find a positive area, we'll make one small change, and that small change is going to be, we're going to just add a negative sign in front of the integral. This will be a negative here. What you're going to end up with is you're going to end up with a negative on the outside and a negative on the inside. And a negative, let's undo those. A negative times a negative is a positive. So I'm going to have a negative number on the outside, and I'm going to have a negative number for my integral. And a negative times a negative is going to be positive. Okay, that's what we're going to do. So if you've got an integrable function f of x with both positive and negative values, we use a combination of this formula and the one from the previous slide. So the integral from a to b was going to be the area above the x-axis minus the area below the x-axis. And remember, this is going to be a positive number here. This is going to be a negative number here. And so what you're doing is you're actually subtracting a negative number, which makes it positive. Well, how does that work? Well, let's look at this guy right here. The area from 0 to pi of sine x dx is 2. So we're told that the area under the curve from 0 to pi right here, this area is equal to 2. So what is the area between the curve and the x-axis? So if we look at something like, take the same integral, okay, and we go from negative pi to pi of sine x dx. The question is, what does that equal? And to answer that question, we look at this area right here, which we were told is 2. This area right here is the same shape, so it's going to be -2. And we just follow our rule that was given to us above. So we're just looking at this rule right here, okay? The area above the x-axis minus the area below the x-axis. So when I do that, I'm going to end up with the area above the x-axis minus the area below the x-axis. And that's going to give me a total of 4 units. And so that is going to be the area under the curve for this particular problem. All right, and finally, one other thing that you can do is you can use your calculator to find the integer, your definite integral on your calculator, and it's going to be function integral or numerical integral, and you can type it in on your calculator. You just need to know what the function is, what the variable is, and where you start and where you stop. And if you've got all of those things, then you can just type it right into your calculator. And there's going to be a separate video for that. It'll be on YouTube and it'll be up and ready to go when you need it. And but it's going to be under the math key, and you can find it in there. If you have a TI Inspire, if you hit the little there's a book on there, the little open book catalog thing, and you can scroll through and find it that way. And I'll do also a video on exactly how to find that on your Inspire as well. So there you go, and that's all there is to using the integrals and kind of how they work. And we're going to learn a lot more about them in the next few weeks.